Hello everyone, it's Dariush and I'm gonna present a paper entitled Zero-Shot Motion Pattern Recognition from 40-point clouds accepted in MLSP 2021. The work has been done by me and my supervisor Professor Stefan Zig from Ambient Intelligence Group at Aalto University. A few months ago, I submitted a gesture recognition paper to a conference, and guess what? I got a rejection. After addressing the comments, I submitted it to another one hoping for an acceptance, but this time, the reviewers, as shown in the right figure, told me how about the unseen classes of gestures. To make a long story short, I managed to publish the paper in the second conference, but it was the beginning of the zero-shot gesture recognition idea. But let's see why gesture recognition is important at all. It provides a device-free and natural way of non-verbal communications. Human-robot interactions, smart screens in shopping malls, both in-cabin and out-cabin vehicular scenarios, and smart homes are a few examples where gesture recognition plays an important role as an interface. But the dynamic nature of a few applications causes the traditional gesture recognition systems fail, given the fact that they might require recognizing a set of gestures that are unseen by the system in the training phase. And as we all know, data collection is a very time and money consuming process which might not be suitable to address the problem. Gaming scenarios, highly dynamic AR/VR smart home applications, and gesture-based interfaces in telesurgery are a few examples of these types of applications. In this work, we utilize Siamese neural networks to propose a novel model which aims to recognize unseen classes of gestures. Here, we have the schematic view of a Siamese network which takes in a pair of moving point clouds representing two gestures and produces a similarity metric. These parallel gesture encoder blocks share the weights, but they perform the computing on multiple instances. To calculate the similarity metric, there are two commonly used loss functions, contrastive loss and triplet loss. You can see the formulas for each on the screen. In both loss functions, the margin M is added to avoid trivial answers. For the gesture encoder part, we propose a graph-based gesture encoder. In the baseline model, the authors apply a KNN algorithm to build a graph from a point cloud, then an edge function to build up edge features, and finally an MPNN approach to process the graph. In the formula below, h of theta is usually an MLP and square function is a rotation invariant function like max pooling. But in the previous model, since there is no time dimension involved, it fails to capture the temporal evolution of the gesture. To address this problem, we propose a KNN approach where the nearest neighbors of each point are found only from the next time frame. The difference between these two approaches is shown in these two figures. In the proposed approach, the trend in the direction of the arrows reflects the temporal dependency, while in the traditional, the connectivity is less and the temporal dependency is not visible. And here, we have the full architecture of the proposed gesture encoder. First, we build the graph from the point cloud through 4D KNN. Then the edge messages are built and aggregation function is applied, and the representation is passed through a few fully connected layers to achieve a 2D representation for each gesture. Our experiments showed that the best results are achieved using triplet loss function with semi-hard strategy and margin equal to 10. What else? As you can see, even for contrastive loss, the online pair selection is better than the offline one. As shown in the right figure, the best value for margin is 10. Here, we have the latent space visualization for the triplet model with different values of margin. As you can see, when we change the value of M from 1 to 10,000, the scale of the latent space changes. Apart from the numerical results which were shown in the previous slide, we can see that the discriminative power of the model when M is equal to 10 is slightly better than 1 and 10,000. In other words, the samples are separated in a better way. Let's discuss the ability of the proposed approach in recognizing unseen classes of gestures. In the left figure, we have a different number of unseen classes from 5 to 17. For each setting, we randomly selected 3 sets of classes for training the model and the rest for inference. As you can see, as we increase the number of unseen classes, the accuracy of the model decreases. Moreover, the difference between those three sets of randomly selected classes increases. Compared to Pantomime, as well as the baseline model, the proposed one achieves higher accuracy with a considerable margin in all those settings as shown in the right figure. In a nutshell, we introduce PGen to recognize unseen classes of gestures, outperforming state-of-the-art models by a considerable margin. To do so, we propose a 4D point cloud processing approach utilizing graph convolution neural networks, which captures temporal dependency in a single pass, achieving up to 60 times less computations and 3 times faster processing times compared to its competitors. Thank you for your attention, and I would be happy to answer your questions and receive your feedbacks and comments.